So our next presenter is Michael Greif. So Michael's doing a Bachelor of Science in Biochemistry. He's been playing around with his presentation a little bit. The one we originally received is what happens when you rub on that cream, understanding how drug molecules penetrate our skin by molecular visualization. And this one's a little bit more technical, visualizing drug permeation of the Stratum Corneum in MDV. And MDV is the Molecular Dynamics Visualization software that was developed here at the HIVE in support of a number of different projects. So it's good to see this particular software suite being used in a wide range of different different applications. So over to you, Michael.
Yeah, putting all that on a screen didn't quite look right, so I changed and shortened it a little bit. They said I'm Michael, and I was focusing on looking at drug permeation through the skin. So one of the reasons why that's important is because rubbing something on your skin is nice and easy. You don't need a needle, you don't need a kid to try and swallow a pill, and obviously if you're treating a skin condition, that's where you want the drugs to be. There's also the skin also is quite a good barrier, so it takes quite a while for the drugs to move through the skin. And as a result, the drugs can be released for quite a long time with just one application. Now that's also a problem, the skin being a good permeator. Sometimes drugs are unable to get to where they need to be, i.e. through the skin. And so one of the solutions to this problem is to attach short lipid tails to the peptide drug molecules that are in question. Cool. I'll just give you a little background about the skin, because that's what I'm going to be talking about. So the stratum corneum is the very outer surface. On that image there, you can see like the skin just flaking off. So it's the part that we look at every day. So the dermis is the part of the skin that is still alive. And as it moves through up into the stratum corneum, the cells slowly get more dehydrated, and they release some lipids that form multiple bilayers between each of them. And so this forms a protective surface that is difficult to permeate because you've got those pretty much entirely impermeable cells that are just proteinous and dehydrated. And you've got many, many, many layers of these lipids that things are going to have a hard time getting through. Cool. So to be able to study this area, we had to simulate the stratum corneum. And so what we have here is just a small section of that area. And so the actual simulation has water above and below it. I've removed that for all of the images that I've shown, mostly just because the water is packed very densely, there's a lot of it, and it's a little hard to see anything through this wall of water. Cool. So you can see the polar head groups at the top that interact nicely with water, the non-polar tail groups that sort of want to come together, and again some polar head groups. So you've got that two-layer system that is happy forming these long sort of membranous areas. Cool. So the molecular dynamics viewer has already been introduced, but it's basically for viewing molecular simulations in 3 dimensions, and that's what I'll be showing during my showcase later. There has been previous work on this by Chris, who's in the audience today. Did a lot of work. So this is high density lipoprotein, I think, and another protein there. So using some of the methods he outlined didn't really work for me, and to understand why it didn't work, I'm going to go into a little bit about the program and area that was used to simulate this. So the program I used was GROMAX, and it's used and it's under the broad heading of molecular dynamics, and molecular dynamics is just computationally simulating molecules, chucking them in, leaving them for a period of time and seeing what they do. So this sort of thing is used when traditional experiments are infeasible. And one of the main uses and reasons why it's infeasible is it's really hard to look at things on a molecular detail through traditional experimentation, especially over large periods of time. So if you want to see that the molecular mechanisms involved, you've got to get a bit closer, and we're simulating all of this so we can see exactly what's happening. The limitations of molecular dynamics is computationally quite intensive. It uses up a lot of computer power. And due to this, simulations are quite short, in the region of microseconds, some of the largest getting up to milliseconds, and they're usually quite small systems. Obviously, the smaller the system, the less time it takes to compute, and even the biggest simulations are somewhere on the order of 1 million atoms. And when you start thinking of even just one cell is hundreds of millions of billions of atoms, you get sort of an idea of why 1 million is on the small side. Cool. So the Stratum Corneum is pretty impenetrable. And because of this, simulating a drug moving through one of those lipid bilayers is going to take huge amounts of time, and simply just putting the drug molecule above the layer and waiting for it to move through it is just not really going to work. And because of that, we've used some enhanced Lani, the person who has done all the real work on this, has used enhanced sampling techniques. And so one of these enhanced sampling techniques is Windows simulations. So basically what you do is you simulate the bilayer and have the peptide somewhere up in the water. You run another simulation where it's just interacting with those head groups. You run another one where it's just begun to enter, another where it's entering, and another where it's sort of stuck between the two lipid layers. And through this, you don't have to wait for the molecule to just move straight through, and you get a lot of energetic and conformational data on that. So what happens when you try and visualize these windowed simulations? Obviously, you've got to sort of paste them together. And the problem is the windows aren't that similar. You've gotten the same system with the peptide at different depths, and let it run for a while, and of course, sort of butterfly effect, all of the lipids have moved around, and so it's quite hard to smooth those lipids being in completely different places. You can see the peptide moving slowly upwards. That's easier to smooth, but the lipids are the real clinchers there. In another way, there's an enhanced sampling technique called replica exchange, where basically you run a lot of simulations that start out the same, and there's sort of different interactions happening in there, and basically they can switch between each other's state. So you have a lot of simulations, they're all switching. The end result of this is you get some you get a lot more movement in the ground state, which is here. Because of that, you can see a lot more detail of what's happening. Now, replica exchange has some of the same problems that I talked about with windowed data. Because they are switching, there is this lipid movement. And so these are like the two main issues that I have been trying to overcome. The way I did this was to remove a large amount of the lipids. As you can see, it's not the prettiest thing, but in the end it does show the conformational data that was really important for this project. So you basically want something to look like is like this. So this is a pool simulation I ran. It is missing some of the information that the replex and window data had. But that's sort of the end result that I wanted to get to. There's still a number of challenges to overcome, to include both the information that was run by the original data and the visual beauty of this simulation. Cool. I'd like to thank everyone at the HIVE, the HIVE internship program itself, the Curtin Institute for Computation, the Pawsey Supercomputing Center, where all of the molecular dynamic simulations were run, and my supervisors and everyone at the Biomolecular modeling group.